If I give you some curve like this one, what is its length? For example, if I imagine this curve being made out of a piece of string and I stretch the string out so it was taut, what would be the length of that string? This is what we call the arc length of a curve. What we want to do in this video is figure out how can I compute exactly the arc length of a curve using calculus. Now, one approximation that I could do, a bad approximation, but nonetheless an approximation, would be to say I can create a secant line that starts at the same spot and ends at the same spot, but is otherwise straight. Now, this secant line is not that great of an approximation, but I can compute it. I know how to figure out the length of a line just by Pythagoras. Okay, what if instead of going and doing the secant from the start to the finish, I broke it up into two different lines, one from the left to the midpoint and the other from the midpoint to the right-hand side? Still not that great. But look what happens if I do 3. Now, if I break this region into 3 different equal lengths, up to the 1/3, up to the 2/3, and the whole way, then the sum of the lengths of the straight lines look like it's getting a better approximation of the original curve. And if I do more, so for example, if I do 4 or 5 and increase the number of subdivisions, I get a better and better approximation. So here's the idea. What I want to do is take the sum of the lengths of all of those straight lines, and I'm going to call that approximately my arc length. And then if I take a limit where the number of subdivisions gets really, really large, we've seen how to come up with limits of sums and replace those with integrals in calculus. This is one of the big triumphs of integral calculus. Let's do the crudest approximation first. Here I have a point AF of A and BF of B. And then what I can define is the change in the horizontal, which is going to be delta x. This is just B minus A. And then there's a change in the vertical, a delta y, which is f of b minus f of a. And if I have my delta x and I have my delta y, then the length of this line, my crude approximation by Pythagoras, is going to be the square root of delta x squared plus delta y squared. Okay, not bad. I can compute it. But let's go a little bit better. Let's do one like this, one where I've broken up into 5 different little straight lines. Well, I have the AF of A and the BF of B, but for all the inner points, I'm just going to go and call them generic x sub I. So there's going to be an x1, an x2, an x3, and so on. Generically, an x value xi. Now, if I try to think about what are my delta x's, what are my delta y's, all of the delta x's I will presume are going to be the same thing. So I'm going to have all of the same delta x's. But the delta y's, the changes in the height, that's going to be different for all the different xi's. Like going from x4 up to b, it's basically flat. There's almost no change in y at all. But if I look going from a to x1, the change is negative. It goes down. So the delta y's are going to be all over the place. Actually, let me zoom in on this picture here. I'm just going to zoom in on one particular pair of them. I have a generically an xi minus 1 going to an xi. The delta x is going to be the same for all of them. If I start at A and I go to B, then it's going to be B minus A divided by n if I have n subdivisions. But the delta y changes because the delta y here is a function of whatever the height is. And so the delta y, I write delta y sub I. What I mean by that is that the change in y, it depends on which interval I'm going to be at. Well, now I have this, I can do Pythagoras, and so I get the square root of delta x squared plus delta y sub I squared. So where are we at so far? The arc length formula that I'm going to begin writing down is the sum of the lengths of all these little line segments. Each line segment is almost the same. It's the square root of delta x squared plus delta y sub I squared. And where it differs is that that delta y sub I is going to be different as we go along. So this is my crude approximation, but I can't compute it easily yet. At least as n started getting really large, it would take a lot of computing what those delta y's were going to be. So to get a better handle on the delta y sub i's, I'm going to use something very important from calculus called the mean value theorem. Now, what the mean value theorem says is that because I have a secant line here, some line that connects 2 points on my curve, is that the slope of that secant line is actually equal to the slope of a particular tangent line. And the slope of this particular tangent line occurs at some spot between the xi minus 1 and the xi. Or the other way to say it is that the mean value theorem is saying that the derivative at this so-called xi star, I put the star there to say at some point, I don't know exactly where it is. I know it's in there somewhere. The mean value theorem guarantees there's a point. I don't know what it is. I'm going to put that little star there. But either way, it's saying the derivative of the function is the slope of the secant line. In this case, the slope of the secant line is the delta y sub I divided by the delta x. So at some point, xi star, I don't know where it is, but at some point, the slope of the secant line is equal to the slope of the tangent line. I can rearrange this formula to go and say that my delta y sub I is therefore the derivative at some point times the delta x. And now I'm going to try to go and stick it down into my arc length formula. So if I leave myself a little bit more space, I can take this delta yi, I can move it down in, and now I have a formula where I don't have any delta y's, it's only delta x's now and the derivative. And the derivative is something I can do with calculus. Notice how I have the delta x squared twice inside of the square root. So I can go and I can sort of pull it out of the square root and it just becomes a delta x. Now, formulas like this we've seen before when we were defining integration. The way we define integration was to take some region, to chop it up into a bunch of points and different points. You'd have a delta x for all the regions. You'd have some function that was evaluated at some point inside of each of those little subregions. That's all exactly what we have here. So if I take the limit as n goes to infinity, I can replace the summation sign with an integral sign and the approximately with an equal sign. So my definition of arc length is therefore going to be that arc length is equal to the integral from a up to b of the same expression, but I've now replaced it with the continuous variable x, the square root of 1 plus the derivative at x squared dx. And that's my formula for arc length. Well, now that I have the formula, let me go and actually do a specific example. So the example that I want to do is the circumference of half of a circle. And generically, if I have y squared plus x squared equal to 1, that's my equation of a circle. And I'm just going to take the positive root, so I get y is equal to square root of 1 minus x squared. That gives me the top half. If I chose the negative root, that would give me the bottom half. Now, we know the arc length of a circle of radius 1. It's 2 pi the radius, so 2 pi. And if it's half of it, it's just going to be pi. So we want the arc length to be pi, but let's see if we get that from using our formula. So if I go and erase this for a moment, I need to take the derivative to put it down into my arc length formula. So I'll take a derivative, minus 2x over 2 square root of 1 minus x squared. The 2's cancel, so I can get rid of those. And then I'm just going to go and blindly plug that into my formula. I'm going between minus 1 and 1 because I have a circle of radius 1. So the x values goes between the minus 1 and the 1. And I put it into the square root of the 1 plus the derivative squared. That's what I get. So let me get rid of the formula, I don't need that anymore, and try to clean this up so I can actually integrate it. Because I have 1 plus something, I'm going to go and try to find a common denominator. I'm going to turn that 1 into 1 minus x squared over 1 minus x squared. Different way of writing 1. Then if I try to make a common denominator and the numerator is 1 minus x squared plus x squared, the x squared cancels, and so all I'm really left with is just a 1 on the top and then square root of 1 minus x squared on the bottom. And this is one that you might recognize. This is the derivative of arcsine. So if I'm going to go and take its antiderivative, what am I going to do? I'm going to integrate it, and it is going to become arcsine of the top value 1 minus arcsine of minus 1. All that remains is to evaluate some arcsines. Okay, so let's move this up. How do we evaluate arcsine? Remember the graph of sine. This is sine, and arcsine is defined to be the inverse to sine on this restricted domain, the green portion, the minus pi over 2 to pi over 2. So, that is, arcsine is the inverse to that little portion of sine. That's how we define arcsine. Now, in this portion, sine of pi over 2 is 1, and thus arcsine, which is the inverse, means that arcsine of 1 is pi over 2. And likewise, sine of minus pi over 2 is minus 1, so arcsine of minus 1 is minus pi over 2. I can plug those in, and what do they get? They get pi. So indeed, we have verified this circumference of a circle of radius 1, or at least half of a circle, is indeed just going to be the value pi. And that means we've got great hope for our arc length formula. Finally, I don't really do calls to actions at the end of my videos. My videos are for my students primarily. If someone else watches them, great. But I will say that I have an app for my phone, so if you leave a comment down below, something doesn't make sense about this particular video or any of the other videos, you can ask questions about it. I will get a notification and I will try to do it. So feel free on this video or any others to leave comments. With that, thank you, and I will see you in the next one.